In this lesson, we're going to learn how to calculate the molar mass of a gas using density information. So as you see in front of you, the molar mass of a gas can be calculated by simply multiplying its density by the universal gas law constant times its temperature, which must be in Kelvin, all divided by the pressure. Now the R value that we're going to be using to solve this problem is going to be our 0.0821, which does have units of liter atmospheres per mole Kelvin. Because we're using that R value, our pressure is going to have to be in ATM, temperature will have to be in Kelvin, and when we calculate a density, it's going to need units of grams per liter. So if you need a molar mass of a gas, you can calculate it if you know the temperature and pressure of the gas and its density, if you know the mass and the volume of the gas that you're dealing with. So the type problem that we're going to solve is we're going to try and determine a molecular formula. To obtain a molecular formula, you need two pieces of evidence. You're going to need an empirical formula first, and we're going to be able to derive that empirical formula with the percentages that are provided. Knowing that our compound is 80% carbon and 20% hydrogen, we can get that first piece of evidence. We can derive our empirical formula. And the second piece of evidence we're going to need is we're going to need the molar mass of this formula we're trying to write. Since obviously we do not know the formula, we can't go visit our periodic table and add up a molar mass, but information has been provided here so that we can calculate the molar mass from the density information provided. And they've also told us that this gas is at STP conditions, so we know standard temperature will be 273 Kelvin and standard pressure will be 1 atm. So if we can gather both pieces of evidence, the empirical formula, and if we can calculate the molar mass, we should be able to derive the molecular formula of this hydrocarbon based on the information provided. So let's see if we can get piece of evidence number one. Let's see if we can get the empirical formula. Given percentages, the first step that you need to follow is you need to get the moles of each of the atoms to write the empirical formula. So if we assume that we have a 100 gram sample here, it's easy to change those percentages to grams. So the 80% carbon becomes 80 grams of carbon. The 20% hydrogen becomes 20 grams of hydrogen. You may recall to actually derive an empirical formula, you need the right units to be able to set up a ratio. Those units happen to be units of moles. So to change grams of carbon and grams of hydrogen to moles, all we have to do is visit our periodic table and look up the atomic mass. For carbon, that atomic mass is 12 grams per mole, and for hydrogen that would be 1 gram per mole. So dividing the 80 by 12 and the 20 by 1 will change units of grams into moles. As you can see, we now have 6.67 moles of carbon and we have 20 moles of hydrogen. To determine an empirical formula, we now simply need to set up a ratio between the moles of carbon and moles of hydrogen. To do so, we divide by the smallest value, in this case that's the carbon. So anything divided by itself, the 6.67 divided by 6.67 gives us that we're going to need 1 carbon. And then if we take the 20 moles of hydrogen and divide it also by the 6.67, we see that we need 3 atoms of hydrogen. So an empirical formula is the simplest whole number ratio of elements in a compound. So we're able to verify that 1 to 3 ratio here between the hydrogen and the carbon. Now that we have the empirical formula, the second piece of evidence that we need the molar mass of this gas. So we're going to use the formula that you can calculate the molar mass of a gas if you know its density, multiply it by R times T, and divide it all by the pressure. So we got to pay close attention to units here. So the mass that was provided was in grams, the 0.488. The volume here was 364 milliliters. We've got to change that to liters. How do you change milliliters to liters? You simply divide by 1,000. So if you take 364 and divide it by 1,000, you'll get 0.364. So our density here in the correct units of grams per liter will be the 0.488 divided by the 0.364. We then need our universal gas law constant, the 0.0821, which once again has specific units, in this case of liter atmospheres per mole Kelvin. Now we need our temperature, and it's stated in the problem that we have STP conditions, standard temperature and pressure. Standard temperature is 273 Kelvin, and then we divide everything through by our pressure, which is also standard. Standard pressure in atmospheres is 1 atm. So you do the math here, and you're able to calculate that the molar mass of this gas, based on the information provided, is 30 grams per mole. So now we have our two pieces of evidence. We have our empirical formula, the CH3, and we now have the molar mass to be able to write our true formula, our real formula, our molecular formula. So we take these two pieces of evidence, we take our empirical, and we take our calculated molar mass of 30. We see that the empirical formula only adds up to be a molar mass of 15. That is 12 for the one carbon and 1 for the 3 hydrogens. That adds up to 15. But we just calculated that the molar mass has to add up to be 30. So obviously to go from 15 to 30, that's a factor of 2. So if you double your empirical formula, the CH3, you'll obtain the molecular formula, the real formula, sometimes called the true formula, of C2H6. So based on the percentages given and the information about the density of gas at STP, we're able to derive that the molecular formula here is C2H6. And this is, of course, the formula for ethane.